All right, the first thing that I want to make sure is that you understand the terminology that I'm going to be using. And so this a to the n, that whole thing is what I'll be referring to as the exponent. Okay, so the exponent is going to be made up of two parts. The base is the number. Remember, exponents represent repeated multiplication. The base is the number that's being multiplied by itself. And then n is the power. I'll refer to this as a power, and that's the number of times that base is being multiplied by itself. So when you look at this exponent here, a to the n just means a is being multiplied by itself, dot, 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 a total of n times. Okay, so again, exponents simply mean repeated multiplication of a base, a total of whatever the power is, number of times. All right, so with that in mind, there's several properties that should be reviewed regarding exponents. And the first is if you have a negative power. A negative power does not change the sign of your base. Okay, that's the most common mistake made on a negative power. What a negative power does is it inverts your base, or it flips the number of your base. So if your base started in the numerator, a negative power will move it to the denominator, and vice versa. If it starts in the denominator with a negative power, it'll move it up to the numerator. So a to the minus n is equivalent to saying you take that whole base a, move it to the denominator, and change the power of its sign. Okay, so this is one of the rules that should be reviewed for you. Okay, now, let me extend this a little bit. If your base is a fraction, and what that negative power is going to do, again, it just inverts your base. So the a was in the numerator, so when we apply the negative power, it's going to move to the denominator. The b was in the denominator, so it gets moved up to the numerator, and you change the sign of that power. Okay? So you're just going to flip your base. Okay, the second property that I want to mention here is when you're multiplying exponents that have the same base. Do you guys remember what you do with their powers? You add them. Again, if you're thinking of this as a cubed times a squared, what that means is a cubed is a repeatedly multiplied 3 times. A squared represents a repeatedly multiplied 2 times. And so the total number of times is just the sum of those powers. So you have a to the m plus n would be your property. All right, so let's kind of go through these sample problems. Okay. So if we take 2 to the minus 4, what you'll often do with a negative power is you use the negative to flip your base. So our 2, in this case, is going to get moved to the denominator. And then we change the sign of the power. And in looking at that, we can now repeatedly multiply 2 by itself 4 times. So 2 times 2 is 4, times another 2 is 8, times another 2, 16. So you'd get your solution 1 over 16. Again, notice the sign of the number does not change. It doesn't become a negative value. All right, if we look at part B here, B, we have just that single base of t. So the negative power is going to move that base to the denominator, change the sign of its power. There's nothing else that you can do to simplify that, so that winds up being your solution. All right, this holds true if your base is a binomial, in this case, if it's multiple terms. So here we just take our base, which is this whole expression x plus 1, we move it to the denominator, and we change the sign of its power. And once again, there's really you don't need to simplify this any further. If you wanted to expand out the base, the denominator, what you could do is applying this square. Now, we haven't talked about this, and we're not going to go through expansion here for another few sections. But when you square a binomial, you can't just apply that square to the 2, or to the x and to the 1. Right? You have to treat it as if you're foiling these binomials. So you have this outer plus inner products that you have to account for. So really, it winds up being another missing term in here if you were to expand that out. So for right now, there's no reason to expand it. I'll accept either form, Okay, but you need to expand it correctly if you try. All right, and then the final example in sample problem 2 is e to the minus 2t. So even if your base is an irrational number, the same rule applies. We take our base, move it to the denominator, change the sign of our power, and again, there's nothing else to do to simplify that. All right. Questions working with negative powers? All right, let's extend this a little bit beyond. I know the sample problems might be out of order slightly, but let's move to sample problem 3. These are all on page 12 of your book if you want to follow along. All right, so if you're looking at this first example here, we're multiplying two exponents with the same base, so what are we going to do with their powers? We just apply this property, add the powers. We get t to the 9. Move on to the second example. The same idea. You have these two bases, or these two exponents. They have the same base, so we can combine or use the property that when you multiply exponents with the same base, you add their powers. So -4 plus a 1. Again, any unwritten power, if you don't see anything written there, it's assumed to be a 1. And then you can simplify what you have. -4 plus 1 gives you -3. So this is one way that you can write your answer. You could also express it with a positive power by moving your base of t to the denominator, changing its sign to a +3. And so either of those would work fine for that second example. And then finally, sample C. All right, when you have coefficients, the coefficients can still be multiplied. These are just factors. This is 10 times t to the -3rd times 5 times t to the -9. So you can rearrange your factors if you want to. So if you mentally think of moving this 5 and this t to the -3rd, switching the order of those, using which property indicates switching the order? You guys remember? You'll be quizzed on it tomorrow. Commutative is the one that switches order. Okay, so we have the commutative property that allows us to take 10 times 5, which is 50, and then we have multiplication of exponents with the same base, so we can write that common base and then add their powers. So -3 plus a -9 winds up giving you t to the -12. Okay, so this would be one form of your answer. Now we could also rewrite this using positive powers. If we did that, what would we move to the denominator? The 50t or just the t? Just the t. The power of -12 only applies to the t. So when we use the property of the negative, the 50 is going to stay in the numerator, but the t gets moved to the denominator. We change the sign of its power. And so either of these forms would work for that.